Anyway, my name is Emily Stolfo, and I'm going to talk about distributed systems and your code. This talk is called Beauty and the Beast. I'm a Ruby engineer at Elastic. Who uses Elasticsearch? Okay, cool, a lot of people. So if you're familiar with Elastic, the company, we have a number of products, and they're all, yes? Did you just remember that you use Elasticsearch? Well, actually, this is a good thing, because you'll see in this talk, I'll talk about how we have very complex ecosystems in our applications. And sometimes you might have Elasticsearch running and be using it without even knowing, amongst all the other 5 databases and servers and services that you're using. So anyway, where was I? Elastic. Elastic has a number of products. They're all based around Elasticsearch, built up around Elasticsearch, the server. I work on the clients team. The clients team writes client code that deals with the Elasticsearch server itself. So there are a number of different clients at Elastic for the other products, but I work with the Elasticsearch team. I'm an adjunct faculty at Columbia University, where I've taught classes on web development, specifically Ruby on Rails, and most recently NoSQL databases, where last spring I gave a kind of tour of different NoSQL databases and talked about different use cases and how you could choose one NoSQL database for a certain use case. I'm a resident of Berlin. I've lived in Berlin for about 5 years, and I'm originally from New York. I love Berlin. And I'm a maintainer of these gems. Sorry, I'm going to move a little bit. These gems, they're all pretty much, they have to do with Elasticsearch. They're divided in 2 different categories. Some of them have to do with using pure Ruby with Elasticsearch, and then some of them have to do with having Elasticsearch be integrated into your Rails application. And I put this little bubble here because previously I worked at MongoDB, and that's relevant for this talk because I worked at MongoDB for 6 years, where I co-wrote the Ruby driver and maintained Mongoid. And so I started at Elastic last June. I've been there for less than a year, but the point is I've had 7 years of experience interfacing with a community of people who are using my code, a client, to connect to a distributed system. And you can only imagine what kind of questions I've gotten over 7 years, what kind of bugs have been opened against the libraries I'm maintaining. And I've noticed that sometimes with a little bit more theoretical knowledge and understanding of distributed systems, their behavior, their protocols, their algorithms, people can write more clever code, and then that would reduce the issues that are being opened against the libraries they have to maintain. So this is entirely selfish. It's just for myself that I'm giving this talk. Okay, so this is my friend Bear, and he lives in Berlin. He's an application developer. And he, like a lot of people, uses a distributed system in his application. But he's never had the chance to really stop and think about what is a distributed system, what are the algorithms, the behaviors, the protocols that it has, and how he can write code that better uses this distributed system. So because he's never had this time to spend to think about distributed systems, he has gone through a number of years thinking that distributed systems are simple. But in reality, distributed systems are complex. And what do I mean by he thinks that they're simple? Well, this is the kind of code that he'll write. He'll write wow, this is really washed out, but you can still see the code. This object DB is a kind of object that you'll get from a client, like the library that I maintain. And this object will allow you to ping the distributed system. So what he'll do is he'll ping it, and he'll get a positive response back, and he says, okay, cool, I can do a write. I can do some other kind of operation. So then he goes and does an insert. This is quasi-MongoDB syntax. So he'll do an insert, and he expects it to work because the ping has returned a positive response. So that seems pretty simple. Distributed system is simple. It'll tell you when it's available, and then it'll be available for your next operation. But this is where distributed systems are also complex. They're complex because there's a lot of things going on that you don't know, and that Bear doesn't know and he doesn't hear about. So for example, taking the same exact sequence of instructions, Bear will do a ping, and then an election will happen in the distributed system, electing a new primary. A primary in this case is the only kind of server that can accept a write. And then he'll do the write, and he'll get a response back saying not primary, or this write cannot be applied because there is no primary at this time. So that's where the distributed system is complex, because it kind of has a mind of its own. Things will happen behind the scenes, and Bear won't necessarily know about them. But another reason that Bear has been able to think that distributed systems are simple is because they're designed so that you think that they're simple, so that Bear thinks that they're simple. That's part of their beauty, and that's part of, well, it is kind of the beast, but it's also kind of the beauty. It is part of their beauty that they take this highly complex thing, this beast, this system that's supposed to do many different things all at once, and only presents to you, the user, presents to Bear, what he really needs to know. So they're actually complex underneath the surface, but they appear to be simple. So you can get away with thinking that they're simple. But even more than that, as I alluded to in the beginning, we're building applications today that are very complex themselves. They're composed of a lot of different services, 10,000 APIs. It's basically Willy Wonka's chocolate factory, 5 different databases. We're using Elasticsearch. We don't even know it. So your application itself might share some characteristics with a distributed system. It might not be a distributed system per se, a first-class academic definition of a distributed system, but it does have some of those characteristics. So it's important to understand distributed systems and some of the theory behind them. So this talk is divided into 2 sections. The first one's the beast, the system. We'll talk about some distributed system theory, like defining it. We'll talk about consensus, synchronization. Maybe some of these things will remind you of what you learned in school that you haven't thought about since school. And if you haven't gone to school for computer science, maybe some of these things will be new to you, or maybe you've only read about them at a surface level. We're not going to talk about security because that's a very complex topic and a whole talk in itself. And frankly, I don't know that much about security. Skipping over that. And then the beauty, which is Bear's code. And so how the beauty can complement this beast. And if we know the fairy tale of the beauty and the beast is actually not really beast in the end. They love each other. They find each other and love each other. So we'll look at errors that Bear gets in his application. We'll look at some of his retrying code, the gems that he uses, and the APIs that they make available and how he can use them more effectively. And we'll look at how he tests and how he can better test. So let's take it back to school. Let's go with the academic definition. What is a distributed system? Well, a distributed system is textbook definition, autonomous computers that work together to give the appearance of a single coherent system. So it's often defined as middleware because you have a distributed system which is a number of different members, a number of different components, but what makes it a distributed system is the glue that pulls them together. So the algorithms, the protocols, the way that they communicate, that's what makes it a distributed system. So it's middleware. It's something that kind of goes in between. And I use this symbol of Cerberus, which might be familiar to you. First of all, it's a beast, so I like this symbol to represent the distributed system. And secondly, it's an entity. It's a single animal, a single beast with multiple heads. So it's kind of like a distributed system because there are a lot of different heads that think for themselves, but they all make up a single whole, a single entity with one single goal or identity. Even further defining distributed systems, their characteristics. So communication between components is invisible. Bear does not need to know how the components of the distributed system communicate with each other. The system's internal organization is hidden. Again, Bear doesn't need to know about this. It's hidden from Bear. It's easy to scale. So taking the Cerberus metaphor, Cerberus can have 3 heads, it can have 13 heads, it can have 30, it can have 300 heads. It should be able to handle all of those heads. Components are independent. Faults are unknown to user. So do you notice the theme here? Basically, one of the main characteristics of a distributed system is a lot is hidden from the user. A lot is invisible. And that's important for Bear to understand. So this is my favorite slide in the entire talk, and it might sneak in other points. It is my favorite slide because it sums up life. Nothing is free, nothing is reliable, and nothing is secure. So these are false assumptions. If any of these assumptions are made and you're developing code for a distributed system, your distributed system will fail. So don't make any of these assumptions if you're developing a distributed system. But you'll see that these become relevant also to Bear's code later on in the talk. Okay, so let's start with the first theoretical concept, consensus. Consensus is about communicating and reaching an agreement. It's kind of abstract, so we'll look at a specific code example. When I show code examples, you can look to the right corner, and I'll tell you whether it's using Elasticsearch or MongoDB. I'm sticking with examples using those 2 systems, because that's what I know best. This one's using Elasticsearch, and terminology. A shard, for people who can't see, a shard is a subdivision of an index. And a subdivision of an index will be kept on one node, which is a member of an Elasticsearch cluster, and the shards will be divided amongst nodes. So in this example, we'll have 2 different shards, and they'll be on 2 separate nodes. So this example, the client will create an index, and if you see right here, moving a little bit, see right here it says wait for active shards. That's an option you can provide when you do a write to Elasticsearch, and that says, tell me whether or not this operation has been applied to 2 shards, but don't necessarily fail if it's not. You can also make it fail if it's not, but in this case, I just want to report back telling me if it was applied to both shards, or 2 shards. So all shards are available, all nodes are available, so it reports that shards acknowledged true. In the second example, I've killed 1 node before I do this write. So I do a similar write. I create an index, test2, same thing, wait for active shards, but I get a response back saying the shards acknowledge false. And so the point of me showing you this is that consensus is something that exists in the distributed system. The communication between nodes allows the distributed system to adapt or notify each other of changes. So bear, I have not done anything here after killing the node to tell the distributed system that it needs to, 1 node is no longer available, update your configs. The distributed system figures that out on its own. And that's where it's really complex. And this is an example of consensus, agreement, communication. So more formally, consensus is used to achieve overall system reliability in the presence of a number of faulty processes. And then some more applications of consensus. We looked at the code example, but some broader, more general applications of consensus are whether to commit a transaction to a database, choosing a new leader, choosing nodes with a particular role in the distributed system. And then perhaps some more real-world applications are clock synchronization, control of drones, page rank, load balancing, these kinds of things. And perhaps the most hip example is Bitcoin. Bitcoin uses proof of work to maintain consensus in a peer-to-peer network. So you know consensus. It's a concept that is very familiar to us. Okay, so we have communication, but that's not the whole story. Being in sync is also important. So synchronization is about having the same information at the same time. And I'm going to talk about this concept of clock synchronization because it's perhaps really familiar to us. For those who don't know, there is something called wall clock time. Wall clock time is the numerical value that I see in my watch, that I see in my computer, that I see in my phone. It's the representation of time that we as humans recognize. But in a distributed system, it's really difficult to have nodes that are not located in the same area. They could be across the world. They could be all in the same rack in a data center. It's really difficult to get all of those servers to have the same exact wall clock time, the same numerical time. So what distributed system researchers did over decades was they thought and they thought and they tried a lot of different ideas, but they eventually just said, you know what, let's just back up and ask ourselves, what is time? And I know this talk is about distributed systems, but I'm getting kind of bored, so I thought maybe we could open up discussion, talk about what is art. Just kidding. Back to clocks. So researchers, they said, okay, so like what is time? Is wall clock time really important to us in the distributed system? No, what we actually care about is more ordering of events. So what we do with logical clocks is we favor the ordering of events, and we basically consider wall clock time irrelevant. Okay, we have communication, we have agreement, we're in sync, but we need roles. Roles are determined by election algorithms. Election algorithms allow the distributed system to assign roles and elect different members to have different roles and have different responsibilities in the distributed system. So MongoDB uses the Raft algorithm. This is a whole talk in itself. But if you look it up, you can find a really cool animation. It should be one of the first results in Google that comes up, so you can see how the Raft algorithm works live. There's also a ring algorithm. There's the bully algorithm. There are a bunch of different algorithms. And again, this is the result of a lot of different research. And basically what Bear needs to know about election algorithms is that his distributed system will have one, and it will allow different nodes to have different roles, and that to be automatically done over time. So if we look at the code example again, we saw this in the beginning. So with elections, the database, you can ping the database and get a positive response back. And then an election for a new primary can start. And as we saw before, that can have effect on the subsequent operation that Bear does. OK, we have communication, we have synchronization, we have agreement, and we have roles. What about reliability? Let's beef up the distributed system. So we need replication in order to have reliability. Replication is the concept of having the same copy of data on multiple nodes in the distributed system. And we cannot have any kind of failover or any kind of nodes taking over for others if we don't have replication. We don't have different copies of data distributed amongst the distributed system. Sorry, I just used the word distributed twice, but you get the idea. OK, so replication is used to increase reliability and performance, but once you have replication, you have this problem of consistency. And consistency, OK, so replication is when you have data that's written to the distributed system, it's distributed amongst the nodes, but you're always going to have a lag, or you might have a lag, and that introduces this problem of consistency. When we have this problem of consistency, we need to categorize it in order to handle it. We need to control it in some way. And what we do with that is we define these deviations of consistency that we're willing to tolerate. And those deviations can be something like staleness. So how old is the data allowed to be? You can have some time limit on the staleness. You can have, this is a little bit more abstract, but you can also have a sequence of operations and say within this given number of operations, I'm willing to tolerate some disordering, so some operations being out of order. And you can also have something which is a little less common, is numerical deviation. So in the case of stocks, or some numerical value, you can say that we're willing to tolerate plus or minus some value. That's less common, though. But the thing about consistency is you can define the deviation of consistency that you're willing to tolerate. But there are a lot of different ways of thinking about consistency. So consistency can be thought about from the perspective of the distributed system, or it can be thought about from the perspective of the application. And when you think about this, you want to define these models of consistency. So you have some kind of guarantees. And it's just not just some random thing like, oh, yeah, OK, eventually it'll be consistent, or maybe at some point it'll be consistent. You want to have some definition, some guarantees for both the system and the person using the system. So there's some consistency models. One of them is called causal consistency. It sounds kind of abstract, but this example will hopefully make it really clear. So causal, sorry, it's not so clear, but I think you can still read it, right? I'll read it through, so it should be clear. Causal consistency basically describes that when you have operations executed in the system, there's going to be some relationship between one operation and a subsequent operation. So there's kind of a vector from one to another. And so in this example, we'll see that in process 1, I write x equals 1. In process 2, I read x equals 1, and then I write x equals 3. If this is causally consistent, then in process 3, I must read the result of process 1 before I read the result of process 2. So in process 3, I read x equal 1, and then x equal 3. Process 4 is not causally consistent because it reads the result of process 1 before the result of process 2. So it's a little abstract, but it basically, just think about it as cause and effect. It comes from this word causal, cause and effect. There's some kind of cause, and then effect, cause, effect, and the system, in this consistency model, it guarantees that that cause and effect relationship will be maintained. And looking at a code example of this, MongoDB actually has causal consistency as an option on a session. And this is one of the last things I did at MongoDB before I left. We implemented sessions in MongoDB and in the drivers. So I actually wrote this code, or I implemented this. But so what it does is it creates a session, and you say you want it to be causally consistent. And then I create a view, which is essentially like a pre-query on a collection, which is like a table if you're only familiar with relational databases. And it passes it that session. And then that view every operation it will do will be causally consistent. So it'll never see the result of an operation before a previous operation. Okay, so that's causal consistency. And this is my favorite kind of consistency. It's called eventual consistency. And I know in French and German, eventual means maybe. Is that the case in Italian also? Yeah, okay. So I'm glad I brought this up because when I did this talk for a German audience, they were like, actually I practiced it with the organizers of my last conference, and they said to me, hey Emily, I don't know if you know, but in German, eventual means maybe, so people might be confused by this. But anyway, eventual, yeah, German. I don't know much of German, but I'm getting there. Do know that.
5 years.
Yeah, 5 years, that's what I've got. Anyway, eventual in English means it will happen just at a non-determined point in time. And that's what eventual consistency is. It basically says, okay, so actually, yeah, an example is if you're updating your profile picture on Facebook, it doesn't really matter if everybody sees that right away. I mean, it shouldn't matter otherwise. Maybe it really matters to you, but for a lot of people, maybe it doesn't matter so much. But so if you're updating your profile picture on Facebook, as long as eventually everybody sees that update, it's okay. It doesn't need to be immediate. And that's what the idea behind eventual consistency is. There's no guarantee in the time frame, but there's a guarantee that it will happen at some point. Okay, so I said that consistency, you can think about it from the perspective of the distributed system, but you can also think about it from the perspective of a client or an application. So that's what they call client-centric consistency. And this is maybe where Bear wants to maybe read some more about client-centric consistency and see how it might be relevant to his application. So you can have something like monotonic reads, monotonic writes, read your writes, writes follow reads. So these are things that are more from the perspective from one single client, but in an application, there might be multiple clients because as requests come in, you might create a different client. But this is important for Bear to know because if he wants some kind of guarantees, client-centric consistency might be what he wants because it's really about one single user's experience of his application and of the system, of the distributed system. Okay, last major subject in our theory and our education of Bear. We have synchronization, consensus, communication, whatever I was just talking about, consistency. And so now we have fault tolerance. Fault tolerance is kind of like Cerberus having 3 heads, and then suddenly he loses 1 head, but he's able to recover from it and still operate as a beastly beast like he is. Fault tolerance is about making faults invisible to the user and recovering from failures. So again, just like consistency, in order to really control this and have some guarantees, we have to categorize the different kinds of faults. So the different kinds of faults are transient, intermittent, permittent. So transient is they're faults that happen like that, and then they go away. So they're not faults that return. Intermittent faults are faults that come, and then come again, and then maybe again, and then eventually go away. So they persist for some period of time repeatedly, but they don't go away immediately, but they also don't correspond to a complete outage of your system. And then a permanent failure is one that happens and is an outage, so you can't recover from it, something permanent. The system really goes down. So in order to handle faults, the system has to have some kind of redundancy. And if you think about it, we have redundancy in real life. We have 2 lungs, we have 2 kidneys, we have understudies for plays, for ballets, for operas. We always have kind of a backup. And in a distributed system, it's important to have redundancy, to have multiple servers, so that some can step in for others. And then when you recover from a fault, when you recognize that it has happened, and the algorithm kicks in to recover from it, you can recover to some state. And the state can be either forwards or backwards. So you can go to some previous state, or you can go to some future state that you haven't seen before. So that's how the system qualifies what it means to recover from a fault. It says, okay, we have this fault, we need to get somewhere stable. We can either go back or we can go forward. And that depends on the distributed system as to how they handle that, which way they go, backwards or forwards. Okay, so Bear understands by now. He's convinced. Distributed systems are complex. But let's look at his code and see how they can be more simple. This is the beauty side of the talk. And you recognize this slide? It's my favorite slide again. So this slide was used to describe false assumptions when you're developing a distributed system, but it's also relevant when you're working with a distributed system. All of these things, nothing is free, nothing is secure, nothing is reliable, are all relevant when you're writing an application that deals with different services, that deals with many different databases, with distributed systems. So let's not make any of these false assumptions. So the first thing for Bear to understand is errors and what kind of errors he can get. They basically come in two different flavors. They can be either network errors or operation errors. In this case, we have, and then network errors are different types. So in this case, we have a network blip. So blip is, Germans also told me they didn't know what blip meant, so I'm explaining what blip means. Blip is onomatopoeia. It's like what it sounds like blip. So a network blip is something that just like happens like that, a little poof, and it goes away. But what's really important to understand for Bear is that the blip can happen on the way to the server and on the way back. And what's the difference between these two scenarios? In the first scenario, the update switch. The first scenario, the update doesn't reach the database. And in the second scenario, the update reaches the database, but from Bear's perspective, he sees the same exact error. So the problem with this is that he doesn't know if his operation has reached the server or not, because the error looks exactly the same. Another type of network outage is network error is an outage. And in an outage, the operation never reaches the server, but he might get the error. The error might look exactly the same as the blip. So sometimes you don't know if it's an outage, if it's a blip on the way to the server or on the way back from the server. And then the second flavor of errors are operation errors. In operation errors, you actually hit the server, but you get an error response back from the server. In this case, it says not authorized. And that means that you need to authenticate or authorize yourself, give yourself the appropriate role in order to do this operation. Or you could get something like not primary. This is taken from MongoDB. MongoDB, if you select a server to send a write operation to, and then an election happens, and that server is no longer a primary, it will return an error to you saying, hey, I can't take this write operation. I'm not a primary. You have to figure out who the primary is and send the operation to that server. OK, so taking those errors, so it's great to, you can catch the errors in the application. Bear can catch these errors in his application, in his code, but how does he handle them? One thing that he could do is retry, because he really wants his operations to reach the server in the most number of cases. OK, so understanding errors and what they mean allows him to write retrying code. But me, as a client author, what I want Bear to understand, and what's really important for everybody to understand, is that the code I write is not going to make any assumptions on what the business logic of your application is. I will do my best in my code, in the client, to get the operation to the server. I will retry if it's something obvious that has not been applied on the server. But I can't make the call as to whether or not it's safe to retry a certain operation and possibly risk having redundant data, so writing the same thing twice. So let's look at an example. This is using MongoDB, and this operation will be an update. It'll match on an ID, and then it'll increment a counter by 1. And it'll be an upsert. So if that document is not there, it'll insert the document. And if this operation happens twice, it'll only ever insert the document once. So what could possibly go wrong? Let's look back at the different types of errors we have and think about how Bear can write retry code into his application in order to get this operation to MongoDB, to the distributed system. So a network blip. Again, remember, this blip happens, and then it goes away. But Bear cannot tell from the error whether the error happens on the way to the server or on the way back. So what's the best way to retry? Or what's if you think about it as the characteristic of a blip as being something that comes and then it goes away, retrying once is probably going to get the operation to the server, because it's not an intermittent error. It's something that happens and goes away. So retrying once should work in all situations for a network blip. But then with an outage you can handle in a number of different ways. An outage, let's assume that an outage can be repaired or can be recovered from, just would take a certain amount of time. So the retry that you would want to do with an outage is to retry with a limit. The limit can be a numerical limit or a time limit. So you can say, I want to retry 5 times, or I want to retry over and over again for 5 minutes. But time limit isn't so great because it really depends on what your application is. If it's a user using your website, you don't really want to make them wait for so long because then you might lose sales. And it's really up to Bear, and it's his call what kind of retry behavior he wants to have for an outage. He could just fail immediately, or he could give his system, a couple of seconds to recover. But it really depends on, again, that's the call I can't make in the client code. That's business logic. Bear knows what's going on in his application, and he knows what kind of retry logic he should have. Operation errors. Again, this is something that is reported from the server. There is no network error. But in this case, not authorized, what kind of retry should you do? What kind of retry should Bear do? With not authorized, if you retry, you're probably going to get a not authorized error again, right? And if you don't, something's seriously wrong. So you probably don't want to retry. Retrying is futile. There's no point in retrying in the case of an operation failure of that type. But then this error, not primary, this error indicates, as I said before, that an election might be in course. So if you wait a little bit, you might be able to discover the primary after that period of time has elapsed. So in this case, you might want to wait and then retry once. So hopefully you see by now that there's no one-size-fits-all for all of these error scenarios and all of this business logic and all the types of operations. But there is a key and there's a secret to being able to write code that covers the most number of scenarios possible. And that's idempotent operations. Who knows what idempotent means? Who knows Latin? Who wants to tell me what idempotent means? Idem means one, potent means power. So it describes an operation that can, it's hard to explain. It describes an operation that can be executed multiple times, but will only ever be applied once. So it's safe to retry an idempotent operation because it'll only happen once, guaranteed. So how do you translate that abstract idea to code? Let's look at a MongoDB example. This is how you would do an idempotent operation and retry so that if you end up getting the network blip on the way back, but you have retried, you can make sure that the first time the operation was applied, there will be no second operation applied. So in this case, this is a little bit of pseudocode because this isn't quite Ruby stuff here, but you get the idea. What's more interesting really is what's happening in the update. So in the update, we'll start with unique. Unique is going to be a unique value. In the case of MongoDB, you would use an object ID. It's a unique value generated by the driver. And you're going to do an update where you match on the ID, and then you add this unique value to a set. A set is a data structure within a MongoDB document. And you have upsert true. And you retry this operation so that it'll only ever be done once because you are matching that ID. IDs are unique, and if it hasn't been applied the first time, then it'll be applied the second time, and you only ever end up with one document. Step 2. You want to do this update where you increment the counter. So we saw this example before, we're incrementing a counter. And to make this idempotent, we match on the ID and the unique value. And then we do the update. And in the update, this is the update portion here. In the update, we remove that unique value from the set, and we increment the counter. And the reason this works is something about MongoDB. The operation, I say we, even though I don't work for the company anymore, but sorry. What MongoDB has is atomic operations. Atomic operations means that it will do this query portion, we'll find the document and do the update in one single step, and no other operation can happen on the system in between those two steps. So you're guaranteed it will match on the document and it'll update it, and then you're done. And it will only ever happen once, because if we get a network error after it has been applied and we try again, it's not going to match in the first part because the unique value has been removed in the second part. So Elasticsearch has something very similar. You can do idempotent operations also in Elasticsearch, and we call it optimistic locking. And the way it works, so again, Elasticsearch, you can see in the right corner. The reason we can do this with Elasticsearch is because Elasticsearch versions its documents. So every document will have a version associated with it, and you can query for that document and find out what the version is. So that's what I'm doing here. I get this document with ID 1, and it reports back the version is 1. So then I use that version in the second step to do an idempotent operation, this update, because I match on the version. So this will only ever match the version once, and then I can safely retry. So let's just say, again, we'll take our blip situation, where I apply this update. It's applied to the server, but on the way back, I get an error. So I retry, and it goes, the same operation goes back to the server with version 1. This is the error you'll get. It'll say version conflict. Current version is 2 because the operation has been applied, but it's different than the one provided that I requested, version 1. So that's why idempotent operations work. That's how it works in MongoDB and Elasticsearch, and I think other distributed systems should have some similar techniques available through their APIs. Okay, idempotent operations, the key to being able to safely retry for bear. I also want to talk about gem APIs because I've worked on gems that interface with distributed systems for a number of years, and I spent a lot of time making APIs so that people can write code to use different techniques and strategies and algorithms with the distributed system. And I've realized this when I'm working in Elasticsearch or working in Elastic on Elasticsearch, that at MongoDB, you can't use MongoDB without a driver. Unless you write your own wire protocol parser, because MongoDB doesn't use HTTP. It uses BSON data messages. So you need a driver to interpret messages and know how to send messages to MongoDB. Elasticsearch uses HTTP. So you can just use an HTTP library to send messages to Elasticsearch. So why would you use a client? Use a client because the client has all of these options available to you and all these behaviors that understand Elasticsearch and do its best to get to we call it sniff Elasticsearch, know what nodes are available, to recover from elections that happen, to expose all of these options that Bear needs in order to use Elasticsearch. And so it's really important for Bear to know his gem, because a lot of work goes into them, to make it even simpler for him. So see how he's been able to get by thinking distributed systems are simple? It's because my code's so amazing. I'm just kidding. No, it's because the gems really do their best to make it easy to use a distributed system. But it's also important for him to understand what's going on in the gem. So what does the gem do in the case of a network blip? What does it do when a primary or leader, or whatever kind of node in the distributed system is taking writes, is not available? What happens with a network outage, if operation failure? These are things that are important for Bear to know about the libraries he's using so that he can write more clever code. And this is a mashup of, to give you an idea of some of the options available in the clients, this is a mashup of both MongoDB driver client options and Elasticsearch client options to show you what kind of things the clients make available to you. So things like retry settings in the driver for MongoDB, you can set the number of retries you'd like to do on a read. I think they now have, since I left, ability to retry writes because they have transactions and sessions and things that have been developed since I left. So there should be a write retry settings also. Things like sniffing is from Elasticsearch. You can determine whether you want to sniff to find out what nodes are available and what nodes aren't available. You can set things like connection timeout. This is interesting. Server selection timeout for MongoDB describes how long you're willing to wait to find a server with a specific role. So with MongoDB replica sets, MongoDB clusters or the distributed system, nodes can have different roles, like they can be read-only, they can be arbiters, where they don't actually keep any data, they can be primaries, and if you want to do a specific operation that you want to do on a node with a specific role, like a secondary, to take the load off a primary, which is taking writes, you can define how long you're willing to wait for the client to identify that node. So anyway, give you an idea of what kind of options are available to you. It's worth checking them out because you can write much better code that's much more efficient and can handle errors and retry better if you're familiar with the options that the gem makes available to you. Okay, last topic in our education of Bear and looking at his code is something that I tell myself all the time. Testing against a single server running on localhost isn't sufficient. I love testing my gems on running against Elasticsearch running on localhost because my tests always pass. But as soon as I introduce a network or I have more than one server in the Elasticsearch cluster, weird things can happen. And me as a client author, I cannot assume, and I should not assume or think that people are always using Elasticsearch on a single node Elasticsearch, because they shouldn't be using that. So I need to test against a Elasticsearch cluster, and you're probably not just using a single host for your distributed systems. You also need to test against a cluster of your distributed system. So do you recognize this slide? I snuck it in there one more time. So my favorite slide again, false assumptions. Change these false assumptions into tests. These are things that I do because I want to see how the client behaves in the face of faults, when the distributed system is doing a failover, when a node is no longer available, when there's an outage, I can't contact it anymore. Turn them into things like this. So the network is secure. You must test with authentication. I love testing without authentication. Everything works great. It's fast. I don't want to use SSL. Latency is 0. Use a network, not local host. I've been thinking about this a lot lately, specifically because I've been building a benchmarking framework for the clients where we're running the benchmarking client code in a single server. And we've had a lot of discussions on the team as to what the infrastructure should look like for benchmarking client code against Elasticsearch. Everybody says, well, we're really interested in only the client here, so we might as well just run it on localhost because we just really want to stress the client code, not really Elasticsearch. But then everybody else, or some other half of the group, was saying, it's really unrealistic, and it would be people wouldn't give credit to our benchmarking results if we're not using a network in some capacity. So what we ended up doing was we have 2 fixed boxes, one for the client code, one for Elasticsearch. So we involve a network, and I put a lot of work into making sure that the network latency is constant. So I have dedicated boxes running these tests, because if you use something like dynamic instances in a framework like Jenkins, where it'll just create servers for you to use and to run tests on, the network latency will be variable from run to run. So this, I know I'm talking about benchmarking right now, but this is relevant also to testing your own application code. You should involve a network. You should involve some kind of cluster, not just a single server. So Bear is feeling a little overwhelmed by now, but he's really happy with a lot of the new knowledge that he has. And he actually texted me this morning, and he asked me, he said that his team is having some issues with persisting to Redis. He thinks that there's a race condition. And he asked me if I would consider putting the Redis persistence code in a mutex, and was wondering if that would make sense. And I know that he, a lot of this information was pretty overwhelming, but I can tell that now he's thinking more about what's going on in his distributed system. So I asked him a bunch of questions, like, what is your Redis topology like? Does Redis guarantee order of write operations? Who is initiating the requests? Where are they coming from? Are they a lot of different services trying to do requests that should be somehow in sync? Has there been any failovers or change of state of the Redis servers? And anyway, we had it back and forth for a while, and I think he was able to resolve the problem. And I look forward to seeing what other things, what other questions Bear has in the future as he really internalizes some of this distributed systems theory. That's it. Thanks.